Hey guys, welcome back to another gas laws video, and this is going to be a fun one because this is the last one. This is the end of our unit, guys. We've covered all the gas law stuff, and so today we're going to talk about two things, but the first one is our ideal gas law. So first, start off, let's recap some things that we know. 1. Pressure is caused by collisions of a gas inside its container, right? So that's what pressure is. The hotter something gets, the more collisions you've got. The more collisions you have, it's pressing outside on that container. That's what pressure is. You feel pressure when you have gas hitting you. It's kind of the idea. So the inside of the balloon, the more air you pump into there, the more collisions you have, and the more pressure it exerts, making that balloon bigger. Another thing we know, temperature is a measure of the average kinetic energy. So it doesn't tell you exactly what the energy is of every single particle, but it gives you an average. Some are a bit faster, some are a bit slower. But temperature is the average kinetic energy of all of your particles. Third thing we know, particles travel in straight lines until they hit something. And so they're going to keep going whatever speed they are till they hit something, then they will transfer some speed maybe and change direction and then go in a straight line again. Now this is all kinetic molecular theory stuff that we talked about back in Unit 1, but just a little recap of it, because it's going to lead us towards something that we know about gases. Now we're going to go back to the 1800s. Our good friend Avogadro, who we know well from Avogadro's number, he proposed that if we had a certain temperature and pressure, which he called standard temperature and pressure, STP, that an equal number of molecules, that's not how you spell molecules, that equal numbers of molecules of a gas would occupy equal volumes. So put this into like easier terms. He basically says, okay, if I had a mole of hydrogen, for example, I've got the same number of particles as a mole of helium or a mole of nitrogen, all these gases. So if it's the same number of particles, it should take up basically the same volume, shouldn't it, if it's the same number of particles? So that was his hypothesis. So we started doing some measurements. He set standard temperature and pressure to 0 degrees Celsius and 101.3 kPa. So that is like the standard temperature and pressure. What would that be? 273 Kelvin and 101.3 kPa. Now, he did some measurements, and it turns out that 1 mole of a gas, and this is not just a gas, this is any gas that is acting in what we call an ideal fashion. So any gas that acts regularly will take up exactly 22.4 liters at standard temperature and pressure. Every single gas, every single time, 22.4 liters if you have 1 mole of it. Now, there are some edge cases where gases don't act properly. They're non-ideal gases. And that can be like if you're under a lot of pressure or like something weird is happening. Or some gases just don't. There are too many intermolecular forces with the gas, so they act oddly. But again, those are edge cases. You don't have to worry about that. For our course, for all intents and purposes, we're only going to be looking at ideal gases. And for ideal gases, 1 mole occupies 22.4 liters. Now, we call that amount the molar volume. It is the volume that 1 mole takes up. So the amount of space taken up by 1 mole of a gas, and the molar volume is always 22.4 liters. Circle it, square it, highlight it, underline it. This is an important number. If I say you've got a mole of gas, you know what the volume is now. So, what is the volume of 0.75 moles of an ideal gas? All right, well, 1 mole, I've got 0.75 moles. I need to change out of moles and into volume. What's volume measured in? Well, liters. And I know that 1 mole is always 22.4 liters. So if you do some unit analysis on this, you'd see that mole and mole will cancel out, and you'd be left with whatever 22.4. You're left with liters. And mathematically, you're just doing 0.75 times 22.4. You don't have to divide by the 1 on the bottom because it doesn't change the answer. So if I have 0.75 moles of an ideal gas, well, it's going to take up 16.8 liters of space. And so you can see that if I had 2 moles of gas, well, that means I have 2 times the volume. If I had 4 moles of gas, 4 times the volume. We can use those facts of how volume and moles increase with each other to derive something called the ideal gas law. Circle it, square it, highlight it, underline it. PV nRT. Super important. PV equals nRT is one of those foundational equations in chemistry. Anytime you're working with a gas, you're probably going to use some form or something derived from PV equals nRT. All of our gas laws, Charles' law, Gay-Lussac's law, Boyle's law, even the combined gas law, they're all derived from this formula. This formula is kind of like a master formula for all gases. So in this formula, P equals pressure, V equals volume, N is your number of moles. So now we can use number of moles. This is what we've included now. This is new. Actually, I guess kind of volume is kind of new. Before you might know the volume of a container, but now we can talk about the volume of the gas because now you can derive that from number of moles, which helps. Temperature of the gas, which of course is always in Kelvin, and R is now some random number. Well, not random number. We're going to figure out what that number is, but it's called the ideal gas constant. Now, if you change pressure or volume or something like that, or temperature, your ideal gas constant will change. And so this ideal gas constant only works at a set pressure and temperature, which is fine because we do a lot of our experiments at standard temperature and pressure. And then we know that our ideal gas constant will always be the same for every gas. So what is it? What is this ideal gas constant? What is it? Well, it's just a number. So let's find out. Let's examine 1 mole of a gas at standard temperature and pressure. Now, why do we pick these? Because 1 is a very easy number to do math with. So what do I know? I know I have 1 mole, which means I know that I have 22.4 liters. I know my volume. And if I'm at standard temperature and pressure, I know I'm at 273 Kelvin and 101.3 kPa. So I know everything except for R. Let's figure out what it is. Pressure, 101.3, times the volume, 22.4, equals N. Oh, sorry, N is number of moles. I know that. That's 1. Times R times temperature. All right, well, I got a 1, and I don't really need the 1. 1 times anything is just going to be itself, so I'm just going to erase that. That's basically gone. If I check the other side, I've got 101.3 times 22.4. Oh, that's not 22.4. There it is. 2,269.12 equals 273 times the ideal gas constant. I just switched the order because it looks nicer. Divide both sides by 273 to get R on its own. And I should get, yep, there it is. R, not dot, equals. So our ideal gas constant, so for any gas at standard temperature and pressure, R is always the same number. It is always 8.31. It's a constant. Constant means it doesn't change. So anytime you're at standard temperature and pressure, you will always have an ideal gas constant of 8.31. Write that number down somewhere. Save it in your calculator, maybe. Remember, we used to use calculator memory? That's one of those numbers you're going to have to be pulling out and using in equations regularly, similar to like Avogadro's number. What are the units of this thing? All right. Well, if I rearrange this equation, and I want to get R on its own, well, I divide both sides by N, and I divide both sides by T. So my units are, well, pressures are in kPa, volumes in liters, number of moles is just like number of moles, it's just a number. Temperature is in Kelvin. So my units are kPa liters per Kelvin. That's weird. What does that mean? I don't know what that means. And you'll find this pretty often with constants. A lot of times the units don't make any physical sense as to what they actually are talking about. It just so happens to be some fundamental number that works in the equation. So our units are kPa liters per Kelvin for the ideal gas law. What does it actually mean for us, though, in terms of how do we use this number? It means this constant only works if you are in these units. So up until now, the only thing you had to watch out for was Kelvin. Temperature was always in Kelvin. Now, in order to use this properly, pressure must be in kPa, volume must be converted to liters, and temperature must be in Kelvin. Because if you're going to plug the ideal gas law into an equation and you want your units to cancel properly, these are what you have to be using. If you're not using it, then your answer will be wrong because your units won't have canceled properly. So make sure from now on, if you have an option, even if you don't have an option, even if it doesn't seem easy, always convert pressures to kPa, always make volumes go into liters. And then you're good to go for your ideal gas law. So for example, what volume will 4.96 times 10 to the negative 3 moles of krypton gas occupy at standard temperature and pressure? Okay, so what do I know? I know, okay, I'm going to start like this. PV equals nRT. Pressure. Well, I'm at standard temperature and pressure, so I know that's 101.3 kPa. That comes from standard temperature and pressure. That's why I know that. My volume, I don't know yet. It doesn't tell me directly. Oh, that's an ugly N. N, my number of moles, it does tell me. 4.96 times 10 to the negative 3 mole. That's right out of the question. R is my ideal gas law. I'm at STP, so it is 8.31. That's from the fact that we're at standard temperature and pressure. We can use the ideal gas law, which means you can use the ideal gas constant. And temperature, well, I'm at standard temperature and pressure again, which means I know what the temperature is. Always 273 Kelvin. I need to figure out volume. So let's do it. Let's plug in what we know. PV equals nRT. Pressure, 101.3. Volume, I don't know. Number of moles, 4.96 times 10 to the negative 3. Ideal gas constant, 8.31. Temperature, 273. All right. Now I look at the right side and I see a whole lot of numbers and I see no variables. So I'm just going to multiply all of this together to simplify it a little bit. 4.96 times 10 to the power negative 3 times 8.31 times 273 equals, so this side of the, so I've got 101.3 x equals 11.25 ... Math advice, guys, you can round your final answer to 2 decimals, but don't round until you're done. So I have more of these numbers here. This decimal goes on and on and on. I'm saving that number in my calculator. I'm not rounding it yet. So when I go divide by 101.3 to get x on its own, I keep that number in my calculator. I just hit divide 101.3. How many moles do I have? 0.11 when I round it to 2 decimals. Moles. It's actually 0.11108 on and on, but 0.11 moles if I round it to 2. So I only round on the very last step. That is accepted best practice. If you round too early, that rounding error can really change your answer. Like if I rounded up here, this would have changed this to 5 times 10 to the negative 3 moles. And when I take 5 times negative 3 and I times it by 273 times 8, well, that error is, or that rounding error is being compounded literally 1,600 times. And so that error gets exploded out and changes your answer quite a bit. So only round in the last step. Okay, so we know that's the ideal gas law. Now we know that molar volume is the volume that 1 mole of a gas takes up. And so an effect of this, one side effect, I guess, happens when you mix gases. If 1 mole takes up 22.4 liters, what happens if we put 2 moles together in the same space? What happens to the pressure? And so this kind of field of study is called partial pressures. Each gas in a mixture has its own pressure that it exerts, right? Because its molecules are hitting the side of the container. It is going to exert some pressure. If I put more gas in there, that gas will also exert pressure on the side of the container. We call each gas's pressure a partial pressure because it's part of the whole. If I have a balloon filled with, let's just call it air, right? there is some nitrogen in there exerting pressure. There's some oxygen in there exerting pressure. There's some carbon dioxide in there exerting pressure. All those gases are bouncing around. So if I wanted to look at just the pressure of the oxygen, for example, I would say, what is the partial pressure of O2? Or what is the partial pressure of the CO2? What is the fraction of the pressure that's exerted by this one gas? So the total pressure, this is actually a really easy relationship, which is nice. It's just sum of the partial pressures. So the total pressure is just pressure of the first gas plus the second gas plus the third gas plus however many gases you have. You just add them together. So it's actually a pretty easy one to work with. Here we go. 3 gases. Mix them up in a sealed beaker. Otherwise, they'll all fly away. One has a pressure of 0.87 atmospheres. One has a pressure of 0.12 atmospheres. And the last one has a pressure of 1.55 atmospheres. So I mix all these up into a beaker. What is the total pressure this is going to exert? Well, it is just the sum. You just add them. 7 and 2 is 9, plus 5 is 14, 8, 9, 10, plus 5 is 15, 1, 2, keep the decimal, 2.54 atmospheres. So the total pressure these 3 would exert together would just be 2.54 atmospheres. Now, it sounds pretty simple. Things will get a little more fun when you start looking at trying to use partial pressures in the ideal gas law, because then you have to figure out, how much of this gas is exerting pressure? Which do I put into the ideal gas law? What do I work with? But a little bit of practice, and you'll be good to go, I'm sure. So this kind of wraps up our gas unit. So thanks for watching, guys. And if you have any questions, you know where to find me.